Hello, everyone, and welcome back. My name is Mr. Cobalt, and I'm going to be going over some acids. I'm going to go over some basics on acids. And yes, that pun was intended. So let's get into this. So, in this video, I'm just going to go over some basics, some fundamentals regarding acids. I'm going to focus on the Arrhenius understanding of acids or the Arrhenius definition of acids. There are a few different definitions of acids, but in this video, I'm going to just going to use the Arrhenius definition of an acid to try to explain the basics on acids. So what is the Arrhenius definition of an acid? Well, the Arrhenius definition of an acid is that any substance that when you put it in water, it will produce H plus ions, or what are also called hydronium ions. So typically when you see maybe in your textbook or on the internet, you might see something like HA written, and it separates into H plus and A minus. That is a generic way of writing the acid. One thing you could see it maybe sometimes you're written like this. If you have HCl, you might see that broken apart into H plus Cl minus, right? That's one way to write it, but that's really not accurate with regard to what is actually happening in water when you put an acid like that in water. So when you put it in water, what's actually happening is something like this. So here you have HCl gas. If I take my HCl gas and I bubble it through the water, then the HCl will react with the water. And what's going to happen is, excuse me, what's going to happen is that the hydrogen from the HCl is going to ionize. So even though acids are not ionic substances, they do ionize in water. So this hydrogen is going to come off and it's going to be added to the water. This water is actually going to pick up the hydrogen. So then this water becomes what is known as the hydronium ion, H3O plus. So now this has a plus charge on it by picking up the positive hydrogen. So then you're producing what is called the hydronium ion, and then what's left behind is the chloride ion in solution. So you'll notice that we have a gaseous HCl, and then we have liquid water, and then we end up with aqueous H3O plus aqueous Cl minus. Now the water is still there, right? That's why it's aqueous, because now we have H3O plus, the hydronium ion, floating around in water. It's dissolved in water, so therefore it's aqueous. Same thing with the chloride ion that's left behind. That is also dissolved and surrounded by water molecules, and so we call that aqueous. Okay, so let's point out a couple of things. So this is our Arrhenius acid, because when you put this in water, it will produce hydronium ions. So any substance we put in water, when it produces or releases hydronium ions or produces hydronium ions, then you've got an Arrhenius acid. And so what is the hydronium ion? H3O plus. Now, a lot of times you write H plus, but what we really mean is the hydronium ion H3O plus. So the H3O plus is equal to or same as H plus. So a lot of times we're just being lazy. We don't want to write out H3O plus all the time. So everyone kind of understands that H plus is actually H3O plus. It's just a shorthand way or a lazy way of writing the equation. But this is really what's going on. So this is really what you want to understand. So you throw an acid in water, the H on the acid gets transferred to the water molecule and then produces hydronium ion. And this, ladies and gentlemen, is your H plus. Okay. So again, it's not really H plus. We don't actually have H plus ions floating around in solution. Oops. We just have, excuse me, we just have hydronium ions. So the hydronium ion is what is actually in solution, not H plus. So I just want to make sure that's clear. Now, when we're talking about Arrhenius acids, well, there's two types of Arrhenius acids that we need to cover. There's the binary acid, and then there's the oxy acid. So let's start with the binary acid. Binary, as the name implies, is that you have two elements. Of course, if it's an acid, it's got to have hydrogen. That's what the hallmark of an acid is. Anything that gives off hydrogen. And by the way, when you write the formula to an acid, you typically write the acidic hydrogens first. The hydrogen that is going to be released is written first in the formula. So here I have HCl. This H here is the only H in the formula. It's written first. That's going to come off. That's what we call the acidic hydrogen. So here we have HF. H is written first. That is your acidic hydrogen. So normally if you see a formula and it has H written first, that's usually a big giveaway that it is an acid. So the binary acids are going to have hydrogen as one of their elements, and then they have some other element, right? And so the generic formula for a binary acid is going to be H plus X, HX, X being some other element, whatever that element is. A lot of times it's going to be a halogen, bromine, chlorine, fluorine, iodine, but doesn't have to be. So here are some examples, right? So HF, hydrofluoric acid, HCl, hydrochloric acid, HBr, hydrobromic acid, and HI, hydroiodic acid. So these are examples of binary acids. Notice they only have two elements, and of course the first element is hydrogen. Now, the second type of Arrhenius acid is oxyacids, or what is also called oxoacids. I don't think this is as common. Oxyacids, I think, are more common, but I could be wrong. But oxoacids is also used. So you might see oxoacids, you might see oxyacids. The idea here, as the name kind of implies, is that these are going to be acids that have oxygen in them. And they have the formula of, again, the acidic hydrogen is written first. So you got a certain number of hydrogens here, HA, with some element you got a certain number of this other element, whatever that is. And then you've got a certain number of oxygens. So you got HA, XB, OC. Each of these subscripts could be some number. Okay. And I want to point out that this other part, whatever follows the hydrogen, this part here, this XO, XB, OC, this is usually some sort of polyatomic ion, right? I don't want to say it's always some sort of polyatomic ion, but it's usually a polyatomic ion. And I'll give you a couple of examples. So here we got HNO3. So here we have H1N, so that would be our X. And we have three oxygens. And you'll notice that NO3 is a polyatomic ion, nitrate. Here we have H2SO4. So again, we have H subscript, S subscript, O subscript. So again, SO4, that is a polyatomic ion, sulfate. And the same thing here. Again, the first hydrogen is your acidic hydrogen. That's the hydrogen that's going to come off and bind with water. So here I have two hydrogens. Those are going to come off, bind with water. And here I have one hydrogen that's going to come off, bind with water to form your hydronium ion. Okay, so here I have this part. So C2H3O2, that's a polyatomic ion. That's your acetate ion. Now, one thing I want to talk about here is that, yes, this could be considered an oxyacid, and it is an oxyacid, but because we have carbon in here, right, with hydrogen and oxygen, this is also referred to as an organic acid, and it can be named in an organic way, right? So this can be considered let me write it out. So there's a couple of ways you could write the formula. You could write it like CH3CO2H, and This part here is important to remember. See, if you see something with a CO2H in it, that's called that indicates that there's a carboxyl group. This is a carboxyl group, and if you see if you see O2H, if you see this group, that indicates a carboxylic acid. You could write it this way too: CH3COOH. Right, same thing. So these indicate carboxylic acids. Again, these are organic acids, and you can recognize it by either CO2H or COOH. If you see that ending, if you see this in your formula, then you know it's a carboxylic acid. So just FYI, but you can write it like that too. So you can call it an oxyacid as well. So with regard to this, I think it would be, at this time, I want to point out the distinctions between monoprotic, diprotic, polyprotic acids. Why use the word protic? Let me go over that really quick. So why protic acid, polyprotic, diprotic? So if we look at the hydrogen atom, your hydrogen atom has one electron, one proton. The one proton is in the nucleus. Your one electron is on the outside. So this would be your H. So hydrogen, no charge on the hydrogen. Now, if you get rid of this hydrogen, if you get rid of the electron, if this electron goes away, then now it's just going to be the proton left behind, or the nucleus, I should say. So it's going to be just the nucleus left behind with no electron, right? So now if I draw this energy level, there's no electron in that energy level. It's completely empty. The only thing you have left is the nucleus with a one proton in it. We know that the proton is positive, so we have H plus, which H plus is just a proton, right? If this is your typical hydrogen, there's no neutrons in your hydrogen atom. It's just the proton. If this was deuterium or tritium, you would have one or two neutrons in the nucleus. But we're assuming for this, most of your hydrogens are in the form where it doesn't have a neutron. And so in this case, all you'd have left is a proton. So we will refer to H plus as a proton, as giving away a proton or accepting a proton, right? H plus is just a proton, right? So we'll refer to acids as being monoprotic, diprotic, or polyprotic, or triprotic, right? So the protic is referring to the number of H pluses that can be reproduced or produced by the acid. So in this case here, we only have one acidic hydrogen, so this would be monoprotic. So this is a monoprotic acid because it's got one proton that it can give off, one H plus that it can give off, right? So we refer to it as monoprotic. This one here, we have two hydrogens here in front. So both of those can be given off by this particular acid. So this is a diprotic acid. So this one here is diprotic. So that would be a diprotic acid. And then you could have triprotic acids as well, right? For example, you got H3PO4, So there's got 3 protons there, 3 hydrogens. You can give off 3 H pluses. So this is a triprotic acid. You could also call this a polyprotic acid. Poly just means many, right? So many protons, more than one. So you could call this one a polyprotic acid. You could call this one a polyprotic acid, right? So poly just means many, or in this case, 2 or 3 protons. Okay, so that's it for the jargon. So the next thing I want to get into is the distinction between weak and strong acids. So stay tuned. I'll be right back. But before I do, there's one thing I want to talk about. So let's go back to this bad boy right here, this carboxylic acid. I want to draw the structure for you so you see what it looks like. So if I draw the structure, it would look like this. Or let me draw it over here. I'd have a carbon with 3 hydrogens bonded to it. I would have another carbon bonded to that with with a double bond O. Let's put 2 lone pairs on there. And then I have my O and then H. So this, ladies and gentlemen, is what your acetic acid looks like. And this here is the acetic hydrogen. That's the hydrogen that's going to pop off. These hydrogens are not acidic. Those are not going to be come off, mainly because carbon is not as electronegative, so it doesn't pull on the electrons, weakening the bond. Here, oxygen is very electronegative. It's going to pull on the electrons and weaken that bond, so this hydrogen can come off easily. So that's your acidic hydrogen in acetic acid. And again, I want to put a box around this part. This is what your carboxylic acid group looks like. So it's got the COOH. So COOH or CO2H. So that's what that looks like there. So anytime you see this in a molecule, you know it's a carboxylic acid. It's an organic acid. Okay, so on to weak versus strong. Okay, let's talk about strong and weak acids. So basically, a strong acid is going to be an acid that is going to ionize completely in water, almost 100%. Like virtually 100% of it is going to ionize. So if you throw in a strong acid in water, the elements that are bonded together in the acid are not going to stay together. Those the acidic hydrogens are going to come off readily, right? They're not going to the hydrogen is not going to stick on the acid. So almost 100% of it is going to be ionized in water. For a weak acid, that is not the case. For a weak acid, if an acid is weak, it's pretty much going to stay unionized. So what does that mean? That means the hydrogen, the acidic hydrogen, is barely going to come off. A tiny, tiny fraction of the weak acid molecules will actually ionize, but most of it, by far the large majority of the molecules for a weak acid, are going to stay in that acid form with the hydrogen intact. So let me go over a couple of examples. So here, HCl is our typical strong acid, and acetic acid is going to be our typical weak acid. So if we take our strong acid HCl and we throw it in water, all of this is going to ionize, meaning that almost every single molecule of HCl is going to transfer the H to water. So you're going to get a bunch of hydronium ion and your Cl minus, your chloride ion. So basically, when you throw your strong acid in water, almost all of this, hardly any of this is going to be left. It's all going to be gone. Pretty much all gone, right? All of this is going to be ionized into these two. So most of this is going to be converted into these two, hydronium ion and chloride ion. you're really not going to have any of this left intact. So this is going to be gone. No more of this. It's all going to be these two. Your hydronium ion plus whatever the anion is. In this case, it's going to be your chloride ion for HCl. And so what we call this is a non-reversible reaction. What does that mean? It means that this chloride ion is not going to be reacting with water to take back a hydrogen. It's not going to reform this. It's not going to go backwards. So this chloride ion is not going to react with water to reform your HCl. It's not going to happen, right? So we call it a non-reversible or not reversible reaction, or we also refer to this as a completion reaction. It goes to completion. It completely ionizes, right? So it completely goes in this direction, right? So we call it a completion reaction. Now, for acetic acid, which is your typical weak acid, the opposite is the case. Hardly any of this is going to ionize. It's not going to really react with water that much. It will, a tiny fraction will, though. So this acetic hydrogen, this acidic hydrogen will come off and bind with water. So water will take this hydrogen away sometimes. There's a small fraction of this where it will ionize. So water will come in, take this hydrogen away, and form your hydronium ion, and then your acetate ion will be left. The anion here will be left. In this case, this will react with water to reform your acetic acid here. So the acetate ion can reform and take a hydrogen here, a hydrogen, this hydronium ion. This can give back the hydrogen and reform your acetic acid. So in this case, for weak acids in general, most of the substance is going to be in this form in water. Most of it is going to be this, not this, right? So when I throw this in water, most of it is just going to stay this way. It's not going to react with water molecules. The water molecules aren't going to take the hydrogen away to form the hydronium ion. But some of it will, a tiny fraction will. So you will get some of these products, but most of it will be in this form here, right? So most of it will be in this form, a little bit will be in this form. So what we like to say that favors the reactant side, it favors this side. Most of it is going to be on this side. For a strong acid, it's going to be by far favored on this side. So very, very tiny amount of this, hardly any, almost zero amount of this, and most of it is going to be in this form with the hydronium ion and whatever your anion is. And again, in this case, we're dealing with HCl, so the anion is your chloride ion. This is not reversible. It's a completion reaction. This is reversible. And so in order to indicate that, we look at the arrows here. So for a completion reaction, a non-reversible reaction, you only get one arrow in one direction. So it goes to the right. So if you only get one arrow to the right, then that means it's a completion reaction. It's not reversible. If you've got this double arrow, though, right? So notice I have an arrow going this way and an arrow going backwards. When you have a double arrow, that indicates that the reaction is reversible and it can go the opposite direction. Okay, so that's the distinction between strong and weak acids. Okay, so when you're dealing with acid problems, you need to determine whether you're dealing with a strong acid or weak acid. That's going to be really important. And there are 7 strong acids that you should know. I believe I go over it in another video, so make sure you find that video where I go over strong acids and I list the 7 strong acids. So you need to know what those strong acids are. And then anything that is not one of those 7 is going to be a weak acid. So here, I want to point out this diprotic acid. So this is sulfuric acid. H2SO4. Now, sulfuric acid is a strong acid for the first hydrogen that comes off. The first proton that comes off is the strong acid, but then after that, you're dealing with a weak acid. So here, H2SO4, that's going to react with water completely, and it's going to go in this direction. So pretty much almost all of this is going to ionize and donate the first hydrogen, one hydrogen to water to form the hydronium ion. And then what you have left is HSO4 minus, this anion here. So this first step in the process of ionizing in water with your diprotic acid, sulfuric acid, that's going to be the first step is going to be a completion reaction. It goes almost 100% in this direction. So when you throw this in water, you're pretty much going to have mostly this. But then now this here also has an acidic proton. This can also release a proton of water. So then this can also react with water in a second step. So the second step would be that HSO4 minus reacts with water. Water is going to take hydrogen away. So I have this water molecule. It takes this hydrogen away to form hydronium ion again. And then you've got the sulfate ion left over. This, however, is very weak. It's a weak acid situation. So this is reversible. So most of this is going to be in this form here, right? So if I throw this in water, I'm going to have a little tiny bit of this form. Most of it is going to be in this form here. And then I'll have a tiny, tiny bit in this form, right? Because this is weak. So this has the double arrow here showing that this part here, the second step is reversible. This has a single arrow here showing that the first step is completion. It's not reversible. It goes completely in one direction. So very little of this, a lot of this. And then some of this, a tiny bit of this is going to undergo the second step, but most of it's going to be in this form here. So that, ladies and gentlemen, is strong versus weak acids. And that's it for this video. I hope you enjoyed the video. If this was enjoyable, if you learned from this video, then please, by all means, like the video. Hit that like button over there somewhere. Also, subscribe to my channel. Share this video with others. Share my channel with others. When you subscribe to my channel, hit that notification bell. When you do that, make sure that you click all so you can be notified by all the videos I put out. Finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a topic you want me to cover, if you have a particular problem you want me to help you with, or a question you want me to help you with, then put that down below in the comment section. I would love to do that for you. Thanks for joining me. Have a great day.